Welcome to the ABR Adaptive Control demo. The adaptive controller that we will be showing is always learning, and we have proven mathematically that the learning is stable. Consequently, we can guarantee improvement over a non-adaptive controller. It's worth noting that the vision system is a deep neural network that we have built for finding objects. The first part of our demonstration shows the difference between current standard control methods, state-of-the-art compliant control methods, and adaptive control methods that ABR has developed. These three different controllers are best understood by interacting with them while the robot is attempting to maintain a target location. So first we'll see industry standard control. This kind of control is position-based, meaning that the controller drives the arm to a specified set of joint angles. The controller will apply as much force as needed to move each motor to the target angle. This is accurate and repeatable. However, it's unsafe because the controller will try to push the arm through any obstacles, such as a table or person, along the way. Safer control methods have been developed which use force control instead of position control. In force control, the controller specifies how much force to apply to each joint to move to a desired target. By using only as much force as necessary to move the arm, the system becomes compliant and safer to interact with. However, for standard force control methods, with an unexpected load, the controller is no longer effective. In general, compliant controllers need to have a good model of the arm and all of the forces on it in order to control the arm well. The same kind of compliance is available in our adaptive controller. However, the difference becomes clear when the 2-pound weight is reintroduced. Changes in the neural activity indicate how the controller is learning to account for the unknown dynamics introduced by the weight, allowing the arm to move to the target. The spiking neural network is updating its connection weights to improve the model of the arm. Even with the adaptation, the arm remains compliant. It has simply learned to increase the forces applied to the motors, just enough to compensate for the effects of gravity and stiction. With the final part of this demo, we're illustrating how the controller can have a practical application by considering robotic tool use. Current control methods, either compliant or non-compliant, have to know in advance all the properties of a tool that might be used during operation. The vision system is being used to calibrate the movements to account for the tool's changed shape. It makes 2 measurements to get a more precise estimate. However, the mass of a tool cannot in general be ignored, since the whole dynamic model of the arm needs to be updated when the mass changes. As seen here, the compliant arm does not perform well when given a hammer, because the mass is too large to be ignored and still perform reasonably. This limits robots to using tools designed specifically for them or which have been extensively modeled. However, when working in a natural environment, the characteristics of a tool are often unknown. A hammer can have many weights and shapes. We'll now switch back to the adaptive controller. With the adaptive controller running, when we give it a heavy tool, on the first reach it has some error, but you can see that it immediately begins to adapt. So it is learning to account for both the shape and the mass of the tool, a tool it has no knowledge of beforehand. You can see improvement after each reach to different targets. We're now loading weights that we've trained on reaches for about half an hour with a hammer. Even though the placement of the hammer might vary, accounting for the mass is most important. Again, you can see on the first reach that it is quite good at handling the heavy tool. This concludes our demonstration of an adaptive, compliant neuromorphic controller. Over the last several months, the ABR team has created the visual system and all the controllers from scratch. To the best of our knowledge, this set of behaviors has not been demonstrated previously in a neuromorphic system. In particular, the continuously adapting motor controller is a unique technology that stands to significantly improve human-friendly neuromorphic robotics.